which is Vishnu.
Okay.
Hello, Vishnu. If you can try to share your screen.
Okay, I'm trying right now. Give me a second.
Very good. We can see it. Great. So we have the final talk of this morning's session, and Vishnu Jejjala will be telling us about knot machine learning. And yeah, so please go ahead.
Thanks, Ajay. Well, welcome to my kitchen. Thanks to the organizers for a great conference, and thanks for the invitation to speak here. I've tried to make this talk accessible to our broad audience, so indeed we can have a mathematical dialogue. So please do stop me if you have questions during the talk. So I mainly discuss work that I've done with my student Jessica Craven and postdoc Arjun Kaur at UBC. The paper appeared at the end of last year, but towards the end of the talk, I'll tell you about some of the stuff we're thinking about. So this is a talk in mathematical phenomenology in a sense. So the idea is we note patterns and we search for an explanation. And machine learning is a wonderful way of identifying patterns of interest. But historically, this has been an approach to mathematics that has been successful in various other contexts. And mirror symmetry might be the prototype example. So Dixon and Lursha, Vafa, and Warner, they noticed that two clavials give the same physics. Green and Plesser developed this theme, and Candelas and collaborators used this idea to solve problems in iterative geometry. The formal mathematical results followed the mathematical phenomenology. The formal results by Gibenthal and Yao and collaborators came several years later. It's in this spirit that we're using mathematical case studies in order to identify patterns and search for explanations as we proceed. So the machine learning, in a sense, is a black box. It gives probably approximately correct answers in many cases. We want to bridge this success of identifying associations to finding new analytic results and methods. And knot theory provides a wonderful playground because the data sets are large and they're also structurally simple enough to address, and there is a physics understanding of knot theory at a certain level. So let me introduce the characters in this play. Knots are S1s that are embedded in S3s, and I've drawn a few examples of knots. So knots are identified by the number of crossings. So the zero crossing knot's the unknot, and then we have a unique knot with 3 crossings, a trefoil knot, and then a unique knot with 4 crossings, a figure 8, and then after 5 crossings, there are multiple knots with the same crossing number. The knots can be drawn in multiple ways. So here are 2 different ways of drawing the unknot. You can disentangle each of these to be no knot at all, essentially. So just by looking at these pictures, it's difficult to immediately identify this as a unknot. And there's been recent other machine learning work on this problem, identifying the unknot in particular. And Fabian in the audience was one of the people involved in this beautiful work. So in order to identify knots, we use topological invariants. One topological invariant is a Jones polynomial. It's independent of how the knot is drawn. And there's a methodology for computing a Jones polynomial. But an easier way, perhaps, of doing this is to appeal to physics. We can calculate these topological invariants using quantum field theory. So in particular, the quantum field theory we're looking at is Chern-Simons theory. So it's very appropriate that this comes up at a meeting at the Chern Mathematical Center. So a topological invariant on a manifold is independent of the metric. In Chern-Simons theory, the natural operators to study are Wilson loops. So we consider some path-ordered exponential of the integral of the connection associated to the Chern-Simons theory. And given these Wilson loops, we can construct knot invariants. The Wilson loop is integrated along a curve. In this case, the curve happens to be the knot. So Jn of k gives us a Laurent series in a variable q, and this is the Jones polynomial that we're looking at. It's the unknot normalized back-to expectation value of given by this path integral. The path integrals over SU2 connections modulo gauge transformations. So Witten developed this association between physics and quantum field theory and this mathematical theory of knots. So the knots that are boxed are examples of hyperbolic knots. And I've written down the Jones polynomial for the figure 8 knot. The variable q is e to the 2 pi I over k plus 2. The k is the level of the Chern-Simons theory. The k plus 2 corresponds to a one-loop correction to the SU2 path integral. The 2 is a dual Coxeter number of SU2. A second invariant is a hyperbolic volume. For these hyperbolic knots, which are the majority of knots, so up to 16 crossings, there are about 1.7 million knots, and all but 32 of these are hyperbolic. These hyperbolic knots have a knot complement, which is S3 minus some small tubular neighborhood around the knot. The knot complement admits a Riemannian metric of constant negative curvature. So the figure 8 and 3 twist knots are examples of this. And Thurston developed this as a knot invariant. So this invariant also has a nice interpretation in terms of Chern-Simons theory. So here, W is a Chern-Simons functional, and we have two complex couplings, T and T tilde. The S, which appears in the definition of T, is typically real in order to ensure the boundedness of the path integral, but we can analytically continue this corresponding to the complexification of SU2. The partition function I've written has a saddle point, and the saddle point has a contribution from a flat SL2C value connection. And we identify this the saddle point with the volume and the Chern-Simons invariant of the knot. So the volume conjecture of Kashayev, Murakami, and Gukov is that if you take colored Jones polynomials, so these Jones polynomials correspond to identifying representation of SU2 in order to do the evaluation. So the usual Jones polynomial is the fundamental representation of SU2. If you choose some other representation, you get a colored Jones polynomial. If you take the colored Jones polynomial in a limit where the color goes to infinity, evaluating the colored Jones polynomial at particular roots of unity recovers the volume. This is conjectural, but we can see this behavior for a few knots where we can compute colored Jones polynomials to large number. One such knot is this knot K0. It's simple in the sense that it has a small number of ideal tetrahedra that triangulate the knot complement. It's an 18 crossing knot, so it's not simple in that sense. If we plot the volume, if we plot the evaluation of the Jones polynomial at various values of the color, we get this plot that Garofalidis and Lon found, and we notice the behavior is not monotonic. So in particular, the small values of the color are not expected to do particularly well in recovering the volume. The volume only is recovered asymptotically for large N. In fact, even for, we see this converging to a value, but the convergence is in fact rather slow, even for this knot K0, which is fairly simple. So the connection between the Jones polynomial and the volume has been developed in various ways prior to our work. So one of the features of the Jones polynomial is that integer coefficients appear in the Laurent expansion. So this is because there's a homology theory, Kavanagh homology, where these integer coefficients arise as dimensions of certain cohomology groups. The This Kabanov homology has a great Euler characteristic, which turns out to be the ordinary Jones polynomial. Now, if you take the evaluation of the Jones polynomial at -1, the root of unity suggested by the volume conjecture for n equals 2, we find that Dunfield found there was a linear relationship between the log of this expression and the volume. So this was for knots up to 13 crossings. Kavanagh also noticed if you take the rank in Kavanagh homology, that is to say the sum of the HIJs, this is also gives you something which is proportional to the volume, and the plot on the right in the black with the black dots is for data up to 11 crossings. So I presented to you a number of characters. The Absurdist play by Luigi Pirandello, 6 characters in search of an author. Here, my author is the neural network. As I've said, there's been some interest in recent years in applying ideas from machine learning and knot theory, and this is there are several other works in this direction, and this is one more work in the spirit. All right, so we'll essentially use neural networks, which was discussed rather extensively in the previous talk, so I'll be very brief here. We essentially feed an input into a connected network of neurons, and by associating this input to some output, we train the network. And we use the trained network in order to make predictions on unseen data. The hyperparameters in the network then are the weights and the biases associated to the different layers of the network. The nonlinearity is given by this function sigma, which operates on the elements in each layer. So the technology for this is rather old. It dates to the 1950s. Rosenblatt, the Cornell Aeronautical Laboratory, the Office of Naval Research, developed a perceptron model, and these are essentially elaborations on that theme. These are inbuilt into Mathematica starting Mathematica 10, so they're very easy to use and to attack various problems with. We just need sufficient data sets in order to do these investigations. So in this case, initially what we did was we fed the Jones polynomial as an input, and we associated to this the volume. The up to 16 crossings, the Jones polynomials can be represented as 18 vectors. There are at most 16 terms in the Jones polynomials, and we feed an input, minimum degree, maximum degree, and coefficients. So a 2-layer neural network with 12,000 hyperparameters and a logistic sigmoid was what we initially used in work with Onkar Parikar. We found that with knots up to 15 crossings, of which there are about 300,000, training on just 10% of the data set gives us a prediction which is correct with 2.45% error. So this is a very good prediction based on a Jones polynomial, which, according to the volume conjecture, really should have no business knowing about the volume to this precision, since the volume conjecture uses the n goes to infinity limit. So what's going on? And what's the source of this error? Well, the Jones polynomial doesn't uniquely identify a knot. For example, the figure 8 knot and the knot with 11 crossings have the same Jones polynomials, but different volumes. In fact, when the Jones polynomials are the same, but the volumes differ, the spread is about 3%. So our neural network is doing about as well as can be expected. So I've showed you an initial neural network analysis for knots up to 15 crossings. The same applies to the 1.7 million hyperbolic knots up to 16 crossings. And we'll use that data set in the remainder of the talk. So what we want to do is we want to reverse engineer the neural network in order to obtain an analytic expression for the volume as a function of the Jones polynomial. And we wish to interpret this formula using the machinery of Chern-Simons theory. So this may be a good place to pause and see if there are any questions. Well, if not, then I'll continue. So we have some inkling of the fact that the Jones polynomial already at n equals 2 knows something about the higher colored Jones polynomials, and therefore maybe the n goes to infinity limit. So if you evaluate the Jones polynomial at -1, and you evaluate the colored Jones polynomial corresponding to the adjoint representation of SQ2 at the third root of unity, you find that there is a nicely quadratic relationship between the two. So this plot is for about 12,000 colored Jones polynomials. We computed n equals 3. There's nowhere near as extensive a data set for these colored Jones polynomials, so we can't do the same sort of experiments we did previously. But we already see that there is some connection between the higher colored polynomials and the lower colored polynomials. So maybe the volume conjecture isn't out of reach. So here's a plot using t-distributed stochastic neighbor embedding. This is really not machine learning. This is a data visualization technique. It projects high-dimensional data down to two-dimensional data while maintaining clustering and correlations between the different inputs. So here we've taken the vectors associated with the Jones polynomial and projected this down by minimizing some relative entropy in order to present this data. One thing that's striking here is that the volume cluster very well in the top plot, whereas the Chern-Simons invariant doesn't cluster nearly as well. So in the generalized volume conjecture, where we remove the absolute values around the colored Jones polynomial in the numerator, we find the volume of the Chern-Simons invariant appearing on roughly equal footing. So it's interesting that one of these seems to be very learnable and the other is not. So if you did the same experiment that I did with Jones polynomial to volume on Jones polynomial to Chern-Simons invariant, you essentially get nowhere near the accuracy that was reported for the volume. So it'd be interesting to understand a little bit about which topological invariants relate to which other topological invariants in knot theory, and why certain things are learnable and certain things appear not to be learnable in this context. Okay, so we'll also notice a relationship between the coefficients that appear in the Jones polynomial and the volume. So the coefficients here correspond to coefficients from either end, from the minimum degree and the maximum degree. And we notice that the coefficients scale with power laws corresponding to the volume. So these are the first 8 and the last 8 coefficients that appear in the Jones polynomial data set up to 16 crossings. And we see it fits these curves very nicely. We also noticed that if we just drop the degrees from the input vector and provide only the coefficients, so that the Jones polynomial is no longer recoverable from the input, the results are nevertheless unchanged. So we moved from Mathematica to Python here, and our accuracies improved slightly. They went from 2.45% error to about 2.28% error. We noticed that the prediction works just as well without knowing the degrees of the polynomials. So this hinted to us that it's really evaluations of the Jones polynomial that might be useful. You can certainly factor out some common degree and take the absolute value that dies. So we use a technique called layer-wise relevance propagation in order to try to reverse engineer a neural network to which we feed a different sort of data. Rather than feeding it the coefficients of the Jones polynomial, we feed it evaluations of the Jones polynomial. And we compute a relevance score that we associate to each of the neurons using the activations, the weights, and the biases. This tells us which neurons in the network are most important in getting the volume prediction from the network. And in particular, it also tells us which parts of the initial input are the most important bits the network analyzes. So here, we basically take different phases at which we evaluate the Jones polynomial, and we feed the network in the real and the complex parts of that evaluation. So we have 10 different knots corresponding to changing the denominator e to the 2 pi I over r plus 2 for different values of p in the numerator. And we see that for all of these knots, the same features in the input light up. So the red gives us the most relevant features of the input. And we notice that these correspond to particular phases that we're evaluating at. So we then looked at various values of the phases, and we noticed that essentially the certain phases are very, very good by themselves at predicting the volume. So we determined which were the relevant roots using layer-wise relevance propagation. We fed the neural network only the evaluation of these relevant roots, and we asked to make a prediction based on that. And we find errors which are comparable to the errors that we get by feeding the network the full Jones polynomial. The interesting thing is that the phases that we look at correspond to fractional Chern-Simons level. Usually the Chern-Simons level is integer quantized, and we'll make some comments about what this means from the perspective of the Chern-Simons theory. All right, so we found the best phase was 3 pi I over 4. And we find that if we plot the evaluation of the Jones polynomial at this particular phase against the volume, this tracks very nicely a logarithmic curve. So the best value of the phase corresponds to fractional level k equals 2/3. And the parameters in the curve fitting we're done using Mathematica. All right, so we find that the error is about 2.86% using this equation that we've developed from curve fitting. And the error in using this equation to predict the volume is comparable to the error in the neural network. And these parameters of the fit are also rather robust if we feed it the data according to crossing number. So we have a great deal of confidence in that this function is making a sensible prediction at some level. So we have to understand the origin of a function of this type. So if we consider various different phases and we evaluate the Jones polynomial at these different phases, we can see where the error is smallest. It turns out the error is smallest at x equals 2.3, which is very close to 3 pi over 4 that we noticed using layer-wise relevance propagation. And the error follows the curve that the data points that I've plotted. So this data, this shape of the curve is sort of ubiquitous these days. It corresponds to a plateau, a ramp, and a dip in looking at random matrices. So this is akin to at least phenomenologically akin to SYK and near ADS2 physics and so on. But here there's no random matrix in sight. But we'll understand the features of this curve, the dip, the ramp, and the plateau using Chern-Simons theory. There's also a new feature, the spike. The spike occurs at k equals 1, corresponding to the phase 2 pi over 3. The value the Dunfield used in his initial analysis relating the Jones polynomial to the volume is the phase that appears in the Jones polynomial minus 1. Okay, so a brief interlude into Chern-Simons theory. We notice that Chern-Simons theory is invariant under the gauge transformation, provided that we quantize the level in integer units. So here, as we've noted, we have fractional levels. So I'd like to make sense of what this means. In abelian Chern-Simons theory, we can somewhat make sense of k equals 1/2 due to essentially the presence of spin structures. And Greg Moore elaborated this in his lecture notes on Chern-Simons theory. But in general, for the non-abelian case, it's difficult to understand what these fractional levels mean. And there's very little literature on this. Witten sort of developed a theory that may enable us to proceed further. So he developed an analytic continuation where we analytically continue the level, and we essentially use Moore's theory, and we use certain integration cycles to compute using essentially Lefschetz thimbles where certain things are dominant. The validity of the volume conjecture in Witten's language amounts to a statement that a particular connection, the geometric conjugate connection, contributes strongly to the path integral in the neighborhood of this gamma, which is related to both the level and the dimension of the SU2 representation in which you're evaluating things. So for the ordinary Jones polynomial, this representation is just n equals 2, and gamma is k inverse. As gamma varies, the analytically continued iteration cycle can pick up contributions from new critical points, or they can lose current critical points. And use a Stokes phenomena as you cross certain Stokes lines in the complex gamma plane. So for integer values of the level, even if the geometric conjugate connection is present in the integration cycle, it cancels against another cycle. For general values of level, a leading contribution rises from two saddles, and it's given by e to the I w evaluated at the geometric conjugate connection times 1 minus e to the 2 pi ik. So at k equals 1, this of course cancels. This evaluation survives in the semi-classical limit where gamma goes to 1 and the level goes to infinity. So in this case, we have some nice contribution to the path integral from a pair of SL2C critical points after analytic continuation. The volume conjecture in this language is essentially a statement that behavior occurs for the geometric conjugate connection for every knot at n equals k plus 2 in the n goes to infinity limit. All right, so we're working with the ordinary Jones polynomial. We notice that special values of the evaluation phase, which corresponds to fractional values of the level, the approximate formulation works very, very well. So we claim the approximation formula works well for levels k, for which the geometric conjugate connection makes a contribution to the Chern-Simons path integral, and its accuracy increases with a fraction of knots in the data set that receives such a contribution. And we can use this idea to explain the shape of the curve that we've seen. So let's do that. So the plateau region, where k is bigger than 2, this corresponds to just assigning to each knot in the data set the average volume of all the knots in the data set. So this gives a 12% error for knots up to 16 crossings, and essentially this corresponds to latent correlations in the data set. The minimum, which occurs near k equals 2/3, or equivalently gamma equals 3/2, means that the Lefschetz thimbles contain the geometric conjugate SL2C connection that we expect in the semi-classical limit for most knots. The region in the dip between 0 and the minimum, here knots retain some knowledge of the geometric conjugate connection even as k becomes small. And this is sort of the explanation for why Dunfield's initial evaluation at a -1 worked reasonably well. The ramp region between 2 and 2/3 is some interpolating regime, and the knots in this region start to lose access to the geometric conjugate connection. And Witten computed that for the figure 8 knot, its geometric conjugate connection appears around k equals 3/2, which is in this interpolating region. So the spike is the curious feature. It occurs near k equals 1. At integer values of the level, we've noticed the path integration receives contributions only from the SU2 valued critical points. So here, no analytic continuation is really necessary. And we lose, because k equals an integer, we lose knowledge of the geometric conjugate connection, and the error therefore becomes high. So the conclusion we draw from this is a geometric conjugate connection is crucial to the success of the approximation formula. The approximation formula works so well because there's this analytically continued Chern-Simons theory sitting around in the background. So there's a physics explanation for the machine learning behavior that we've seen. So we can ask, our reverse engineered function gives an error of about 3% compared to 2.3% for the neural network. And the error in the neural network is essentially intrinsic to the nature of the data set because the Jones polynomial wasn't uniquely identifying. We can ask whether we can do better with some other formula. We essentially, eyeball the formula and we curve fit to that. So is there a way to assess how well we're doing? We can, define new measures that do this. Fischbacher and Munkler were in communication with us to suggest these new measures. The nice feature of this measure is that it's shift rescaling invariant, and we can ask whether new functions we can use do a better job at minimizing these other measures. By this measure, our neural network gives an error of about 0.033, while our approximation formula gives an error of about 0.068. So there's some room for improvement in the approximation formula that we've written. But it's remarkable that a function with only 3 fit parameters works so well in approximating the volume of a knot. We've seen that in doing other experiments, the different representations of the Jones polynomial work just as well. So, for example, I get a representation which is rather compact in starting with the degrees and the coefficients, or just the coefficients. But if I write out some longer expression that assigns some number to each possible degree, that works just as well. Other polynomials, the Kavanagh polynomial and the Hanfly-PT polynomial, perform with similar accuracy. The Hanfly-PT does less well somehow, even though the Jones polynomial can be obtained as a limit of the Hanfly-PT polynomial. The Chern-Simons invariant in various experiments we have attempted does not look to be learnable from either the Jones polynomial or these other polynomials. We can just use symbolic regression on the data we've got, and the accuracies are fairly good, but there's really no interpretation we can assign to the symbolic regression formula that we obtain. So prospects for future work. We'd like to investigate various inequalities that arise in characterizing the volume in terms of the Jones polynomial and its coefficients. We'd like to use numerics, perhaps, to study the Stokes phenomena in Chern-Simons theory. We'd like to establish some monotonic version of the volume conjecture by playing with perhaps Jones polynomials at higher colors and analyzing them using similar methods. We'd like to learn whether there are similar relations between other topological invariants that have been computed for knots. From a machine learning physics perspective, we'd like to understand what problems are learnable. And here, the failed experiments may teach us something. It seems that it often happens that, typically when someone writes a paper applying machine learning into physics, you apply it to a problem and you report a success. We try various things in order to find a success, but I think understanding the failures are just as useful. It might be interesting and productive to just create a database of things we've tried and hasn't worked in order to maybe understand better the delineation between problems that these methods are successful at attacking and the other problems. We like to, of course, reverse engineer other machine learning results in a similar way as we have this one. One thing that we're looking at recently is applying these ideas to the 4-dimensional smooth Poincare conjecture. The conjecture is that a 4-manifold with homotopy type S4 is diffeomorphic to S4. Friedman proved that it's homeomorphic. The next step is a diffeomorphic. This is equivalent to asking whether S4 admits exotic smooth structures. A particular invariant, which is related to Kavanagh homology or Lie homology, the Rasmussen S invariant, can't be used to detect counterexamples. One way of proceeding, proposed by Friedman and collaborators, and is to find candidate knots that are topologically slice without being slice. So a slice knot is defined as follows. S1 is embedded in S3. This S1 can be regarded as the boundary of some disk, just like S3 can be regarded as the boundary of some four-ball. If this disk is smoothly embedded in the four-ball, then the knot is said to be slice. Topologically, slice is a local type of condition rather than the stronger condition. So Manuelsko and Picarillo earlier this year identified candidate knots that if one can study their sliceness, one may be able to find counterexamples to the Smith-Poincaré conjecture. I think these knots did not work eventually, but it may be interesting to use machine learning to identify further interesting knots to look at. And this is work I'm thinking about lately with Jessica and Arjun, but also with Mark Hughes. So I'll stop there. Thank you very much.
Thanks a lot, Vishnu, for a very interesting talk. Are there any questions? Maybe I have a sort of very broad question relating back to what you had at the very beginning. So you started with a volume conjecture, and
yes,
and then you went into machine learning methods to think about it in relation to knot invariance. Right. Would you say you found evidence in favor as a result of your work, or not?
I would say yes, in the sense that already at low color, you're able to find the volume as a simple consequence of knowing the Jones polynomial. So I think this is strongly suggestive that the volume conjecture is on the right track. I mean, I think most people believe the volume conjecture. The experiments that people have done with knots like this knot K0 strongly show that as n goes to infinity, you're approaching the volume from just plugging in to the Jones polynomial. I think that it's difficult to prove, of course, but it's I think most people believe the volume conjecture. I think this is corroborating that even the Jones polynomial itself knows something, and that continuation sort of gives a physics language for describing why it knows something.
And would there be any ideas for how to prove it from this kind of machine learning effort?
I think if we can find a monotonic version of the volume conjecture, that might be easier to address. And for that, we need data sets for higher colored Jones polynomials. We're in the process of constructing such data sets to see whether we can do this, but we don't have huge amounts of data here yet.
Okay. Any other questions? If not, let's thank Vishnu again, and this wraps up this morning session. Thank